All right, cool. We are good to go. Well, hi everyone. Thanks for coming and joining for today's biweekly PyHC Telecon. We won't have another one for a hot second until probably later April. The next few weeks, starting next week, I'm going to be on vacation out of the country. So we'll just take a little pause while I'm gone and then start it back up as soon as I get back. All right. Um, that's all I have for the moment. Sean, would you like to go ahead with any big announcements and then some of the overview you were going to give us?
Yeah, absolutely. So I have been over here at work building some new things for PyHC, and I wanted to show off the latest thing that I built, the PyHC documentation hub. And I shared that in the Slack channel, like I think last week, so maybe a couple of you have seen it before. But I just wanted to take a minute to show it off, demo it, make sure people are aware, and maybe get a little bit of feedback. And I won't take any more than like, 5, 10 minutes doing this and then turn it over to Steve, which will probably be cooler. But let's see. I'll share my screen first so we can get to what I'm looking for. Um, all right. We're looking at the PyHC website, hopefully. Yep. Cool. So down in our news section here, the latest blog post we have is introducing the PyHC documentation hub. And this is available right now at pyhc.org/pyhcdocs. So I'll click that and then boom, here it is. And essentially what this is right now is it's basically just pulling together all of the read the docs from every PyHC package that uses it. So right here, you'll get a little introduction blurb saying what this is. Try it out in the search bar. Um, we have the available packages in the hub are all listed here, and it's most PyHC packages, honestly. There's a few of them that don't use read the docs, but any of these links will link to the documentation. So these are all going to be, read the docs, documentations up here. And these aren't going to be, but whatever kind of documentation there is, we've linked to it. And yeah, pretty straightforward. I see a chat come through, so I want to make sure. Cool. Thank you, Nick. And yeah, obviously the big thing about this is the unified search. So I've found this personally helpful for myself already in finding, features or functionality across PyHC, and I'm hoping other people find it useful. One example that I went through myself not that long ago, which was just theoretically, I would assume a PyHC package out there somewhere has the ability to find sunspots in images of the sun. I didn't know off the top of my head which package could do that, but you know what? Let's just try this here. If we had this docs hub, we could just go sunspot, search it, and this is basically the same read the docs interface that you're used to, but I've actually recreated this all from scratch because this is not hosted on Read the Docs, if you've noticed. So the benefit of building it from scratch is I'm able to organize all the search results by package up here, which you could never do on Read the Docs, and that's kind of fun. So just going through this naively, Plasma Pi happened to be the first one that came up here, but that doesn't quite look like what I'm looking for. So I could go to the next tab. I'm seeing some SunPy time series things, maybe next tab. Oh, there it is, finding sunspots using Stara. So you click it and look at that. I have the code and sunspot finding. So there you go. One place to do this kind of searching. Just a little bit of implementation details. You do have recent searches over here once you've stopped searching things, just like how read the docs search works. If you wanted to do other things like where could I get MMS data from, you could do that and start to see examples. Implementation detail is they do return results 50 results at a time from the read the docs API. So I can click here and load the remaining pages, and it just kind of adds to the tabs if more packages get pulled into the results. And look at this. Apparently, these are all the PyHC packages that deal with MMS data, minus maybe a few that aren't in Read the Docs. But yeah, so I'm excited that this tool exists now. I had a good time building it. This was, like I said, a total custom implementation. So I actually could go ahead and start taking the documentation from any of these packages that aren't on Read the Docs and kind of squash them into the API results I get from this search somehow. So maybe hopefully sometime a few months down the road, I can just have this linking to literally all PyHC documentation, not just the Read the Docs ones. But yeah, that's pretty much what I've been working on and what I built here. Any questions or comments on that? I get a silent golf clap. I like this.
Also, we should advertise this, maybe like from uh, these from our packages, like have a link to this documentation hub.
Yeah,
Is
I think I saw Nick didn't Plasma Pi open a GitHub issue to do just that.
Yes,
I thought that was
because
very
because I open an issue, that means it'll get done. So
absolutely.
this is extremely useful. So my thought is this an argument for um, making sure that everything in PyHC puts their documentation into Read the Docs?
Hmm. I considered that. And I think we've even had that same discussion at like, spring meetings and stuff like that. Um, if people wanted to immediately play along nicely with what we have here and just join this, if you did move over to read the docs, it would take me literally 2 seconds to add you to this website. But I'm not sure that I want to force people who like other things like make docs to to have to use that. Like SpacePi's documentation is actually very good. I like going through it and how it's organized. It just happens to not be read the docs. So I want to maybe go a step toward trying to see what kind of web scraping I can do to add non-read the docs documentation into my own search before making a new rule like that. But it is convenient that most people kind of already self-selected read the docs.
I mean, like this could be a recommendation, right? For the um, yeah, along with everything else PyHC does, like if it's not already, then you could say like use PyHC because use read the docs because we make your project instantly searchable, easily searchable.
Yeah, make it more like one of the recommendation kind of things,
Yeah,
like a best practice.
yeah. I was trying to find some documentation this morning for SolarSoft software, and it was very, very painful because there's nothing like as easy as this. So
Oh no. Well, I'm sorry I didn't announce this just a few hours.
no, no. It's SolarSoft IDL software.
Oh,
So
okay. Yeah,
I'm
so it
just
wouldn't
saying, like the need to look at documentation is there.
not going away.
It's not going away. No. Great.
Well, hey, I don't want to steal too much time over from Steve here. I'm excited to hear that talk. So maybe like one or two more comments or questions if anyone has any.
This is awesome. And thank you for putting it together.
You're welcome. All right, going once, going twice. Thanks, guys.
Thanks, Sean. Excited to see this come together even more with the other packages.
Mm.
Uh, all right, Steve, you're officially up.
Hi, everyone. I was gonna say, Sean, I was texting with a colleague of mine saying you have to go check this out. So it is very cool. Um, and I will say, yeah, thank you so much for having me. And I'm really excited to be here. I'm really excited about all the stuff that PyHC does. And so it's great to talk with you. Um, Nick, I don't know if you can bring up my slides. Um, I did quickly throw together a set of slides based on some of our existing talks. And so some of this might be things some have seen it before, some of it might be new stuff. I'm going to try and go through it quickly so we can get to questions because I'm sure you probably have lots of questions, and I'd also love to hear more from you. But I'm okay.
I don't know if Julie, you have like a good way. I think I can only share it like
Yeah.
or if one of you. Otherwise, I will just do. I'll
I
just talk a little bit and then open up for questions.
I can, you're talking about the slides, right? I can share that.
Yeah.
Cool.
Okay. You can also share the link to the slides in the chat if everybody else wants to access them.
Yeah, you know what? I'll do both. Second. There's his slide links. Then, all right. Oh my gosh. I have a lot of windows open in front of me. Boop. Now my question is, can you see a presentation
Oh.
mode?
And you can,
No.
yes,
Good.
we can
It's
see
fine.
it, but I have the wrong title there. So um,
Okay, no worries.
that was a talk I gave last week, but it's the right slides. So why don't we just go to the next one, and I'll do the introduction, and that's a better looking slide as well. And so yeah, thanks so much everyone for having me. I'm Steve Crawford. I'm the Senior Program Executive for Data and Computing as part of the Office of the Chief Science Data Officer. I lead the open science implementation. And for today's talk, I'll basically be going through some of the highlights of open source software for NASA, and then some of the stuff that the Office of the Chief Scientist does. And so, yeah, please feel free. As I said, I'm going to try and go quickly through the slides to leave plenty of time for discussion. But please feel free. This is my opportunity to talk to you, and your opportunity to ask me and interact with me however would be most helpful to you. I love starting off my talks with this image. It's an image of Buzz Aldrin on the moon doing a solar wind experiment during one of the EVAs in July 1969, because it highlights two of the things that are so important about NASA, which is exploration and discovery. So, as we do our exploration around, outside of Earth, so much of what is important is actually the science that we do with that exploration. And all of the work that science does and that NASA does is powered by software. And so if we go to the next slide, software from the very start has been what actually has enabled NASA to do the science that's doing. And here, example of some of the Apollo software, which was all made open source and is actually available. And this is some of the early work done by Mary Jackson on the computers at the Langley Research Center, or on Margaret Hamilton and her team writing the Apollo software. Everything from what we do in our missions and our science is all driven by software. And that's even true today as we go to the next slide. And if you click on this one, there should be a good, hopefully, video that comes along with it. Or if not, we'll just keep talking and I'll explain that in this video, you'd see the Ingenuity Mars helicopter take off and lift off on the surface of another planet. Ingenuity made its first flight in 2021. And underlying the flight control software was the open source software F Prime. This was released by JPL in 2017. And that's one of the things that actually helps control the Ingenuity spacecraft. But it wasn't the only open source software package on that project. On the next slide, the Mars Perseverance mission was actually powered by open source software, which had more than 12,000 people that contributed to it. From widely used, packages that are common across open source, to very specific packages like F Prime. And it was actually great to see GitHub and JPL recognize the more than 12,000 people that contributed to those open source dependencies that made the Ingenuity helicopter and the Mars Perseverance mission so much of a success. Without a doubt, and on the next slide, we just have a sampling of the wide range of open source packages that NASA uses. Everything from, once again, the software underlying and that powers just even software development, to things which actually build websites, to modern data science, to great projects like Plasma Pi used in our research. we have a very wide range of different open source software that really powers so much of our software. And if we go to the next slide, and this is probably a group that, I probably don't have to talk too much about, but, just to actually really highlight some of the advantages of open source scientific software is that it increases reproducibility, increases reuse, provides ways for curation and archiving of the software. One of the most important parts of using open source in our scientific software is it provides better understanding of the results, and it also makes it easy to provide credit for the contributions of different groups and people. And we do have a range, as we show on the next slide, of software as part of the scientific process. This stages of reproducibility in terms of our software can go from software is not mentioned, software is mentioned but not described, the software is described but maybe only made available on request. The software is made openly available and citable with a permissive license, with good documentation and testing, and or it's contributed even as a bonus to a generalized package, making it even more accessible. And this is a range and stages of different different types of software. And as we want people to move along that spectrum of levels of availability for that software. And when software isn't made available, there are challenges in reproducibility. The data and plots are shared, but it isn't clear how the plots are derived from the data. Maybe it isn't clear what factor was used in converting between flux units. What often can happen is a scientist leaves the field or the software is lost. The algorithms are described, but with insufficient detail. Configurations or steps are not shared. They might say they use the software, but not how it was run. And then also not citing the software used. And so we're not actually giving credit and also tracking the provenance of how a step or a process was done in the scientific process. Fortunately enough, with technology advances in the last 20 years and different things in the open source movement, there are tools for open science making it easy to share your software and make it more available. And on the next slide, talk about some of those tools. Oh, sorry. Actually, before that, also, before talking about some of those tools, we'll also talk about some of the challenges of open source. And when talking about open source and open science, you can't get by without an XKCD comic. And this one actually does a great job of summarizing those aspects of that so much of our digital infrastructure does depend on a single project being maintained either by a small group or even a single individual. And we do want to actually give credit and for those that are working on that. But there can also be other issues that people come against, which is, for example, sustainability. How do we actually maintain and support projects in the long run? Providing training. These are actually skills which need to be developed, but aren't usually normally part of maybe a normal academic education. Questions around licenses and intellectual property. These are things scientists never get trained in, but are actually important in actually making sure how we make things available. Basic things around, and I shouldn't say basic things, but sometimes because they can actually sometimes be quite complicated, but issues around software engineering, like release processes or best practices in testing. One thing and something people that can happen and people are worried about is you release that software, but it gets misused. We do know that you can't always capture or test for everything, and you can't account for how people will actually use or misuse it. And we should also always be concerned about security. While our scientific software may or may not have direct security implications, there are a range of software that can have security implications, especially depending on what areas you're working in terms of what information should be shared or what information should be protected. And so these are things that have to be considered in part of the development of open source software for science. And then on the next slide, I do have some of the tools that do make this easier. And probably some of these, hopefully you're familiar with. And if you're not, then some opportunity to take a look at some of these different ones. And so a lot of modern software is using version control platforms like GitHub, GitLab, or Bitbucket, which allow you to actually control and how you're actually doing revisions to the software and to actually collaboratively develop the software. There's also great solutions for software archiving, including Software Heritage, Zenodo, and things like the Astrophysics source code library, along with other resources that are hopefully being further developed as well. And then we also have software publishing and curation, and that here you have things like the Journal of Open Source Science, the Science Explorer, and the Science Data Engine, different publishers like the AAS, and that accept papers on software, and that these actually provide ways to actually both discover and describe the software that you're developing. So that's a very quick overview of some of the kind of open source software aspects and related to software and NASA. Wanted to also talk about some of the resources and some of the things that the Office of the Chief Science Data Officer are doing to actually help make open science and our sharing of things like software hopefully easier, along with supporting innovative data science implementation. And so if we go to the next slide, I'm going to also now quickly go through some of the things and work of the Office of the Chief Science Data Officer. The OCSDO was set up to enable groundbreaking discoveries by expanding the availability and utility of NASA's scientific data. The OCSDO provides leadership across NASA's Science Mission Directorate to make scientific processes more efficient through data and computing systems, innovative data science techniques, and transparent open science practices. And so we work across our 5 different our 5 different divisions within the Science Mission Directorate, working with biological and physical sciences, heliophysics, earth science, astrophysics, and planetary science to actually enable those sciences to make their data and their scientific results more accessible. On the next slide, we talked through some of the different areas where we really are focusing our efforts on, and this is in core data and computing, the continuous evolution of our data and computing systems for efficiency, sustainability, security, and scientific integrity, our data science innovation, advancing scientific discovery through innovative applications and partnerships in data science, advanced analytics and artificial intelligence, and our open science implementation, supporting transparent, trustworthy, and reproducible science through open science tools, practices, and guidance. And I'll go through each of these a little bit more, but on the next slide, kind of talking about, the overall, some of the overall aspects, especially related to data, that NASA's Science Mission Directorates produce. Each year, we have over 10 million unique visitors to our data sites. And so taking a look and investigating what different data we have. In fiscal 23, we had over 140 petabytes of data, which we're expecting by fiscal 29 to go to 500 petabytes of data. We typically ingest about 50 petabytes of data per year and have over 1.5 billion total files. And so efficient data management and computing are essential for NASA's missions. And we have our different data repositories in each of our different divisions, which are doing a great job of making that data more widely available. On the next slide, we go into some of the aspects of our core data and computing services and the goals of actually looking at how we're making our data and our scientific computing more accessible. And so, providing, the high level goals are providing accessible scientific data and computing capabilities to support an efficient scientific processes within SMD, providing unified infrastructure to help make interdisciplinary science easier and faster, and enable innovation, infusion, and user experience improvements faster and more uniformly so that all can benefit. We have a lot of different work going on in this area right now, but on the next slide, I highlight a couple of our different areas. And so one of them is the Science Explorer. If you're familiar with ADS, this is an expansion of ADS to all of the different SMD divisions, so including Earth, planetary, heliophysics, along with astrophysics as well. And so this has a very similar interface, but allows search over NASA publications and not only just NASA publications, but over all publications in Earth and space science. If you probably many of you are familiar with this in the heliophysics community, but if you're not, I really recommend taking a look at it in terms of making discovery of publications much easier. We also have the NASA Science Discovery Engine, which provides search over all of NASA's data and providing discovery over 95% of NASA data. And the Science Data Portal, which is at science.data.nasa.gov, which is providing basically a unified experience in actually providing access and availability to discover different sources of NASA data, including and different NASA data repositories, along with different applications that make data more accessible. And so that's a great place and a great first place to stop when coming and looking to NASA data. On the next slide, I talk a little bit about our goals of our data science innovation, which is to develop a comprehensive strategy for driving innovative data science and AI ML initiatives, implement and maintain robust data services and infrastructure to support scalable and efficient data science operations, and provide data governance practices and foster the growth of artificial and machine learning, ensuring compliance, innovation, and readiness for the future. One of the major activities on this we actually highlight on the next slide, which is our AI ML 5+1 strategy. The OCSDO will provide AI expertise, system engineering, infrastructure, and training to facilitate the development of 5 foundation models at least in each of the divisions. And so these are foundation models in each of the different divisions that will use, basically produce generative models that can then be used to produce generative models to actually produce innovative science using very large underlying data sets. We've also produced one large language model that should be applicable to all divisions as well. One of the things that we're currently working on right now, and I can talk about on the next slide, is producing a heliophysics foundation model. And so this is initially using some initial data from SDO data sets to provide ingesting the enormous amount of solar observations that have already been obtained to produce multiple applications that can be generated from this, both on solar wind, on magnetograms, on coronal identification, and other further estimates, that can be actually used and generated based on the development of these large foundation models. If this is something you'd like to learn more about at a future PyHC meeting, I can definitely suggest some people to come talk about it. If already, although I know probably some of the members here are probably also involved with some of the efforts around this. Our final element within the OCSDO is on our next slide, which is our open science implementation. And this is focused in 3 areas, which is policy, funding, and software. And so really looking at, for policy, about how we make our information available through our mission data, our scientific software, our research publications, and our research data, about how it's openly shared and how we can actually enable this process from start to finish. We also provide funding, and I'll talk about some of the opportunities that we provide to help support open science across all of our different divisions. And we also help support software, both directly through funding, but also helping advocate for software across the Science Mission Directorate to help improve the processes around it. To highlight some of that, on the next slide, for example, last year we hosted the Software for the Science Mission Directorate workshop. This was organized by Rebecca Ringet, and so I'll definitely give her kudos for the effort in leading this workshop. But one of the things that we did produce from it is a workshop report of some of the ways that at NASA centers and NASA missions we can work to improve software across how we're actually developing it and making it better for those who are working in software and in software aspects. In the next slide, we highlight some of some of our funding opportunities. And so this is always an important thing to highlight. And which is what do we provide support and funding to? We have a number of different activities, and so these include the topical workshop and topical workshops, symposiums, and conference calls, which was previously F2. TWISC is now an independent call. This helps support open science events. And so things like if you do actually have something like a hackathon or other open science, a data challenge, other similar types of open science events that you're interested in doing, we support them under the TWISC call. We have our open source tools, frameworks, and libraries, our F7 Roses F7 call. OSTFL is our kind of very large solicitation and supporting sustainability of open source tools, frameworks, and libraries. And I'll talk a little bit more of that in the next slide. There's the heliophysics division asked me to highlight the heliophysics tools and methods call. And if you go back one slide, I'll go through the rest of the slides and then go to the open source science call. Sorry. I know I said next slide too early. That was my fault. But thank you for advancing. But the HTM, the heliophysics tools and methods, which is also there to support development of innovative software. We do support the development of citizen science projects, which is supported from the science engagement branch and across our different divisions. We have within the OCSDO 2 additional calls, which is the high priority open source science call, which supports innovative new ways to support open science. This provides seed funding for open science calls. And I believe Julie has gotten one of these calls to help support software in heliophysics. And so she can tell you more about her experience, but I'm very excited to see what is being developed there in support of heliophysics software. And we also have a supplement for open source science and cloud computing. This, for existing grants, this provides a little bit of additional funding to make your existing activities open and available. But one other thing that it does provide, and I'll highlight this as it's currently undersubscribed, is also provides cloud computing credits. So if you do have use of cloud computing and need credits for it and an existing NASA grant, please reach out and talk to me because we're interested in supporting computing for our different projects. On the next slide, I have a little bit more detail of our open source software and science funding. As I said, this is one of our larger calls where it's been supporting about $3 million per year in a variety of open source projects, ranging from some of the ones that are underlying all of the Python data science community, including NumPy and SciPy, but also then with some which are specific to certain divisions. And on the next slide, I do highlight SunPy, which is one of the projects which is supported from here. And I probably don't need to explain SunPy to anyone in this community, although I will I will mention that when I was looking at this slide, I did discover it was established in March 2011, which I think does predate the AstroPy project, which I think is, at least to me, it was a very neat fact. And one of the other things I did look up while looking at this, and I think really should be celebrated by the project, is that since 2020, it's been cited over 300 times. It has over 600 forks. And when I did a search on import SunPy, it was used over 6,000 times in codes on GitHub, and just shows, I think, the tremendous impact that the overall Pi heliophysics community is having through projects like SunPy to actually support the scientific advancements of NASA. And so both to SunPy and Pi heliophysics, I will definitely say thank you for the great work that you are doing. And so I have a couple of slides to wrap up here. And so on the next slide, talking about some of the policy work that we do. And one of the things that we help support with making our information more available is our Open Science and Data Management Plan, which are a part of our Research Opportunities in Space and Earth Science, or ROSES calls. The OSDMP is basically how you explain how you'll be sharing your data and software and publications as part of your proposal and your plan for making that information more accessible. These are a required part of ROSES, and they're part of the merit evaluation of the proposal. They're typically about 2 pages. There's no requirement to fill in the full 2 pages, but that's available there for you to complete writing up the information that you need. But the OSTMP basically includes how publications will be made publicly accessible, what data will be used and produced and made accessible, and what software will be produced and made accessible. So basically explaining what your plan is for how you're making available the scientific information that you're producing as part of your proposal. We have released a common template that can be used across all of SMD, and that's now available on the ROSES OSTM page, along with links to further information. And so that's available and hopefully will be useful for you. If you do want actually more training on OSDMPs, we also have that available as well. And one of the things, as we kind of work on our open science policies, we do actually want to see how we're doing. And so on the next slide, we do actually have one of the examples of our metrics on open science. Last summer, we had a fantastic intern, Becca Milkinson, who came in and helped us actually do analysis on how we're doing with our adoption of open science best practices. We sampled 30 papers across our different divisions from 2023 that cited NASA funding and evaluated whether the data and software underlying the paper were shared in accordance to SPD 41A requirements. Overall, what we found, and which is really, really great, even 2023, before any of these open science requirements were, added to our ROSES call and other aspects, already many in the community, and actually most people are doing open science than not. And so we actually see it being widely shared. Data sharing is more common than software sharing, and different divisions are different stages of adopting open science practices. I will mention that the heliophysics community is probably ones that are further behind than some of our other groups. And so, the work that you're doing to actually make, both our make our software more accessible, and the best practices in sharing that software that I know many in this community are really doing, I know is really going to help here in the long term. And so really appreciate, once again, the work that many here are doing to make this accessible, and really look forward to, as we assess this over the years, to see how that evolves. And so on the next slide, I just have our wrap up, and if you actually want to keep up to date with what the OCSDO and what NASA Open Science is doing, we do have a monthly newsletter. Likewise, if you have things that would be useful to share with the NASA community on new things that are released or new functionality, we would love to share it in the newsletter. And so we're always looking to tell your open science stories. And so if you do actually have things that are updated or things that would be actually worthwhile to tell to a wider audience, please send them to us so we can actually help share it. And please do subscribe if you're not already to our monthly newsletter, so you can actually hear the latest and greatest stuff that'll be coming out across NASA in open science. And so with that, I'm gonna stop there, and thank you very much all for your attention. And thank Julie for handling the slides.
Of course, happy to help.
Yeah, thank you, Steve. That was awesome.
Do we have any questions or comments for Steve?
I do. So do you anticipate that the OSTFL will be solicited in the coming year?
No, it will not be solicited in ROSES 25. Our current plan for OSTFL is to solicit it once every 3 years. So ROSES 27 is the next, or at least the currently planned next time we will be soliciting it. But
Okay, thank you.
yeah, but I will mention that HPOS is always open. That's a no due deadline date program. And so we, and the next due date deadline is, there isn't necessarily, as I said, it's a no due deadline program. So we do regularly review proposals, although there are certain times that we are more likely to review proposals, and March 31st is the next kind of, if you get it submitted by then, it will be reviewed in the next group of reviews that we do. So that's and that's in 2 weeks. So if you are interested in that program, I uh, uh, consider submitting it by then. But it's always open.
Any others? Sean, you unmuted.
Yeah, I've got a number of questions here, but trying to let other people squeeze in for me. Um, Going back here, I'll ask this one first. I think it's easier. Going back to the search and discovery tools you showed off, the three ones there. I remember hearing about the NASA Science Discovery Engine at like an AGU talk, probably the last 2 years that I've went, and I hadn't actually heard of the other two before, so thank you for including them. Are all of those production ready and like deployed already, or are they still being developed internally?
Yeah, they're all production. So Science Explorer, you should, um, yeah, unfortunately I don't have the chat here on my phone, but otherwise, so it's basically, actually the first place to go to is science.data.nasa.gov. From there you can discover everything. So um, that yep. So Julie dropped it in there. And from there, you have the links to search data with the Science Discovery Engine. There also should be links to the uh, actually, we've integrated search between the Science Discovery Engine and the Science Explorer, but you can also go directly to the Science Explorer, which is at scixplorer.org. So also, if you just Google Science Explorer, that will come up. Um, the and so yeah, all of them are live and ready. I was going to say, Sean, actually, the person I was texting was the lead of the Science Discovery Engine.
Oh yeah.
And so I might connect you with them because I think they'd be very interested in the things that you're doing. And it sounds like you're interested in it as well.
Yeah,
Uh,
exactly. I mean, I brought together some documentation in the search engine, but you guys are bringing like all of NASA science together in a search
yeah.
engine. It's so much more impressive.
Yeah. And so I'd love to connect you. But yeah, so this is all stuff which is currently released and available. um, you know, and very much usable right now.
Cool. Well, exciting. Thank you.
Yeah.
Someone else raised their hand up, so I'll turn that back over.
Yeah, go ahead, Matt.
Um, that was great, Steve. Thanks. One of my persistent challenges as a modeler, and I know a challenge shared by other modelers, is making my data available. Say if it's on the order of a terabyte for a big model run. And I did have to step away for a moment at your talk, so maybe you mentioned something in your slides, but I'm not really sure what to do about that, and I don't know if anybody knows what to do about making that available. I mean, I don't feel great just making the code and all the input scripts and everything available, because that requires somebody to have access to potentially thousands of cores on a machine. And if they can get to money for cloud credits, that's nice. But yeah, so I think you understand. I think I've described it enough.
Yeah. Yeah, no, I think, and this is one that we've do have outstanding at kind of providing more guidance for, especially for the simulation community, about what are the expectations and what would be useful and what are the services to actually help make that data more available as well. And so a couple of things that I'll mention here is, one thing is, so for SPD 41A requirements, we, for existing code, for existing code, we don't require that to be made openly available. We just encourage it. And but making that available and making your you know, scripts and how you actually run it available is actually really helpful in terms of reproducibility, even if people can't rerun it themselves, because there's oftentimes so having the scripts available makes it really helpful in terms of reproducibility because people can see how it was run. Making the code available is also really helpful in actually in aspects of reuse and learning. So being able to actually read someone else's code, even if you never expect to run it yourself, helps you actually really very much learn about, how they actually did something and how something is working. And so I do really encourage making that software available, even if you don't expect anyone else to be able to rerun it, either because it's too complicated or even because it requires too much resources. But there's a value in learning from it. For the data, one of the things that we say, and the code and the term that we kind of repeat over is scientifically useful. And so, what scientifically useful means in different areas means different things. But really asking yourself of like, is making this data available scientifically useful? And would another scientist consider this to be scientifically useful? That's kind of the kind of question to ask yourself. And, with simulation data, a lot of it might not be very useful beyond, that initial simulation, or it might not be useful to make the whole data set available, but only the end results or one step of it. It also might not make it useful to preserve it long term because, in 5 years, it might be either easy to reproduce it or completely out of date. And so, that's why we have the Open Science and Data Management Plan for you to describe, from your perspective of like what is making it scientifically useful, and then for that as part of the review process to be assessed by your peers, because I can't, say for my experience is all in observational astronomy. For me to say what's useful in or to provide a single guidance for what would be useful in theoretical heliophysics or simulation heliophysics, it wouldn't, would, we'd rather the communities kind of, be able to actually produce what is scientifically useful for them. But we are hoping to provide some further guidance, working with Jared Bell, and among other people to, basically look at further, what are both what further guidance would be helpful, and then also how to meet the long-term needs of data storage.
That makes a lot of sense. Thanks, Steve. Yeah, and I do like the idea, and I'm glad you mentioned just making certain snapshots, say like the initial and final components or time steps of a simulation, if that's how your simulation works. Yeah, I think that's great advice too. Great, thank you.
But I do encourage that to be a conversation that you have with your community, because I think that's what what would be actually useful there of what would help your community and making that what would making what available would be most helpful to your community, and having that conversation with your peers.
Any other questions? If not, we can ping back to you, Sean.
Hey, yeah. Let's see. On the AI and ML 5+1 strategy slide you showed, I've heard about these for a while. I was at one of your AI conferences, I think last year. They're not released yet, but have you tried a beta version of any of them in your position?
A number of them, actually, 3 of them are released. So, and they're up on Hugging Face. So
Oh, okay.
there's 2 Earth Science ones and the LLM one, the large language model. The Privy model is basically was trained on a large amount of Landsat data, and so Earth imaging data. That has actually even been used by others. So it was initially put together in basically this large model, and then with some additional training, you can use it to do different applications like burn mapping or flood mapping. Another group, I believe they were from South Africa, just took it and used it to do locust mapping. And so, they're made available. You can do the training on top of it to do other features. And, that one was made available. There's also one made available on long-running Mira climate data set. And then Indus, which is the large language model, is also available. There was actually a recent, there was a longer paper describing it in detail, but there was also a recent kind of short note in AGU by Rahul Ramacharity and Caitlin Bugby on kind of some of their experiences with using that so far. We'd love to get more people using them. When the heliophysics one comes out, we'd definitely love to have people using it and trying it out. These are all being made open source, and all being made available on Hugging Face once they're available.
Beautiful. You said the big LLM one was called Indus, right?
Yeah, INDUS.
Okay, great. That's what I found in my quick Google search there. So I'll look into that later.
Yep.
You said you could connect us with someone who could give a talk on the Heliophysics Foundation model. Who would that be?
Let me check with Matt McClure about who. So Matt, some of you must know Matt, or at least hopefully some of you might know Matt. He was a previous kind of data officer in heliophysics. He's now currently the lead in the OCSDO for the data science implementation. And I'm going to check with Matt. If anything, I would actually say Matt, or if not, Matt will suggest somebody. Because I'm just not, off the top of my head, I'm not sure of the right person. So, but Matt should be able to make a recommendation. I'll connect him with Nick and Julie so they can have someone come out and talk about it.
Yeah, great. Because I think me and Julie are already in agreement. We want that to be a telecon.
Yeah, and I'm, I know it's currently in the work in progress. I don't know about the date for it, and so, but Matt probably could actually comment on, and whether or not, I imagine once it's released on beta, that might be a very good time, or released openly, that might be a very good time. But they also might have interest in having some people involved earlier. And so Matt will be a good person to talk with.
Great. Well, hey, thank you so much.
Yeah. I should say, yeah, I also don't know, Jack might also know more details. And so don't also want to leave out anybody.
I've got a name in mind, but I think Matt is probably the best. I think he's been tracking this effort more than I have, so I think he's the best person to ask.
So I have a question again.
Oh, go ahead, Nick.
So a lot of the PyHC packages were created years before PyHC began in 2017. And thus, one of the big challenges that we've been facing as a community is interoperability. So packages like SunPy and SpacePy tend not to work to play that well with each other. Do you have any advice on how to improve interoperability, slash what funding mechanisms might be available in the next 5 years?
So depending on the scope, I'll start with the first one because I think that's an easier question. Depending on the scope, the heliophysics tools and methods and the high priority open source science. So HPOS is about 100K for 1 year. And so if there is specific work that could be done under that, I would suggest considering it. The HTM.
You're asking about funding that licensing.
The HTM is a little bit, I think has a little bit more, larger resources per year, for a little bit bigger project. And then the other question of compatibility, I think this is always something which is can be difficult to work on just because you have different projects, you can have different priorities, and compatibility is not necessarily something which is directly funded or easily funded. And so this is one of the reasons I would suggest something like HPOS as an effort. Or the other thing is, there are the one thing, at least in terms of compatibility, is having, and projects like this, is having a specific goal. So why do you want that compatibility? What is that going to enable for a mission, for a research project, for something else? And being able to actually specify a specific goal of like, if we get these two things to work together, this will enable this specific project. Because that then gives a concrete thing to work towards and to enable. And because I've often run into and in previous lives worked on different things that we've always had conversations around. We should make these two things work better together. And we then a year later we have the conversation of we should make these two things work better together. And the things where I've had seen success is where you have a specific driving need for why they should work better together. Because that then basically gives a reason for people to work on it. And having a personal motivation for, I really want these things to work better together. And so that's just a little bit of a or a answer from personal experience.
Awesome. Thank you so much.
Yeah. Well, once again, thank you all so much for the work you're doing. I'm a very big fan of PyHC, and if there's anything, that's one of the things, the kind of, I always mention, like, as a program officer, I'm here to help the community. And so if there is things that you could use help with, it's kind of like the secret sauce of office hours. Coming to talk to your program officer and is a secret sauce that can help, that might not always sometimes help right away, but is a way to enable help in the long term. So please definitely feel free to reach out to me and let me know what I can help with.
Awesome. Thanks so much, Steve. And yeah, we'll reach out to you again for the email for the name you gave.
All right. Thanks so much.
All right. Have a good day.